Okay, we have done angular motion, right, in the last lecture. So now we move on to one step further to study this thing called the rolling motion. So basically, literally, it's really studying something rolling. Okay, rolling down the slope, something like this. And then also, hold on. A rolling motion, um, something that is rolling down the slope, that is rolling motion. I'm sure you all know what is rolling motion, just that we are going to study the dynamics of it. Okay, so some assumptions that we are going to make. Homogeneous rigid body, that means the whole material, right, is the same. Okay, same density throughout. Okay, that's homogeneous. High degree of symmetry. For example, cylinder, sphere, all of them have at least one or usually more than one symmetry lah, okay? So you can imagine a sphere is symmetrical from any direction, right? You can roll in any direction very easily, okay? High degree of symmetry. And then here we will be studying first for now, rolling without slipping. That means this object, right, it will start to roll down, but it does not slide. So the contact, right, is always in contact. Okay, you can imagine if something, the surface is very rough, something will roll down without sliding. If you are sliding on something very smooth, not just the thing will roll, but it may also slide. That means you overcome the static friction already. Okay, that's the later part of this. First part, we'll be looking at rolling without slipping. And then also for now, rolling motion along a flat surface. Flat surface is a perfect flat surface like this. Look something like that. So rolling motion will look like that with the angles involved. When the cylinder rotates through an angle theta, its center of mass moves a linear distance s. So for example, imagine this is a ball, right? It rolls from the solid part to the dotted part. When this happens, it would have rolled angle theta to cover a distance of s. You see the center, right? Move from here to here. Okay, this distance, right, is s. Why is this distance s? Because you see from here row to here, it follows this arc length. Okay, the arc length, the point of contact starts from here. After that, it rolls, right? It will be the point of contact here. And then actually that's this part. Okay, this part will be touching here. So this whole thing, right, given by the arc length is S. Okay, so the center to the center will be the same as the arc length of the theta involved. All right, by geometry. So these are the formulas involved. S equals to R theta. This one we already know. S is the arc length. And then radius, that's R. Theta is this angle in radians. Okay, in radians. Then the velocity of the center of mass. So this point move from here to here, right? We want to know the velocity. What do? We will go and differentiate S. All right, quite standard. You have S, you will differentiate, you will get velocity. Okay, so you write ds dt, then that ds, right, you change to rd theta from here. Okay, you change it. So this right part here will be d theta over dt. Okay, and that will be your omega. Remember, you differentiate your angular displacement, you will get angular velocity. So in the end, you will get something like this. VCM equals to R omega. So this is the velocity of center of mass, would just be your radius times your angular velocity. Okay, then in the same manner, to find acceleration, same thing, you differentiate your velocity. Okay, you differentiate your velocity. Then from here, VCM, equals to R omega, right? You just put inside here again, the same steps. Then this d omega over dt, that is your alpha. Okay, you differentiate angular velocity, you are going to get your acceleration, angular acceleration. So in the end, you are going to get ACM equals to R alpha. Okay, so these three equations, they relate the quantities for the center of mass, the linear quantities, to the angular quantities, okay, for rolling motion. So some characteristics, all points on a cylinder have the same angular speed, but different linear velocity. Remember when we study circular motion, right? All the points will have the same angular speed or angular velocity, but every point will have different linear velocity because the one closer to the point of rotation will be going slower, right? The one furthest is going to move much faster. Okay, so they have different linear velocity. The linear velocity of any point is in a direction perpendicular to the line from that point to the contact point P. So imagine this thing, this is a cylinder, right? That is rolling to the right, okay? So every point of the cylinder will be rolling in this manner, okay? In the red lines as shown. Then the rotation, right? At this instance, the point of rotation, the axis, is actually this point of contact. Can you see? It's almost like the axis of rotation is here. Then this whole cylinder, right, is rotating around this axis. Okay, so every point here will rotate around this axis. So what the second point means, right, is from any point on the cylinder that's rotating around this point, if you draw a line to the point of rotation or the axis of rotation, the actual direction that that point is moving, right, is actually a right angle from that. Okay, so for example, point Q, a straight line you draw to P, right? Then to find out where point Q is going, is actually just a right angle to this imaginary line to point P. Okay, that's why it's moving here. Same thing for this top P prime, right? If you draw imaginary line is going to go down. That's why it's moving forward. Okay, so for some other random points like this, the line is here, it's going to be moving at a right angle. That's why at that particular instant, it will be moving here. The next instant, everything will change already. So we are talking about exactly at one instant. Okay, this thing is rolling at that instant. Then for here, it will be moving down. The vector will be pointing in this direction. Okay, so it's perpendicular to the line. At any instant, the part of the rim that is at point P is at rest relative to the surface because slipping does not occur. Okay, so this point P, now we are doing rolling without slipping, right? That means this whole thing only rolls. It doesn't slide across the ground. Okay, so at any time, right, this point P, this point of contact, it is not moving. That's why you see this point P, there's no vector arrow there. It's not moving, right, at this instant. Okay, so that's a characteristic also. We will later learn that this point is the instantaneous center of zero velocity. So this point P, right, later when we learn about mechanics of machine, we will learn this more generally again, okay? We'll learn this in a more general form. This is actually the instantaneous center of zero velocity. From this term here, right, you can also guess why is it called that, right? At this instant, this point, right, has no velocity. That's why this is the concept that we'll be touching on next time. Okay, so the same object, let's say it's moving to the right, it will look something like that. Let's say if you go and put traces on this object, right? If you go and trace the center of mass, it will go in a straight line. Okay, the CM, which is center of mass, will appear like it's going in a straight line. If you go and trace this top point here, right, P prime, it will look something like that. Okay, like something bouncing like that. Okay, because it's rolling. Okay, from the top, you'll move to the bottom and then move to the top, move everywhere. Okay, so it's going to look something like that. So now we're going to move into how to calculate, how to solve problems regarding rolling motion. Okay, rolling motion with center of mass moving at VCM equals to pure translation with speed VCM plus pure rotation with omega equals to VCM over R. In other words, right, a rolling motion is just a combination of two motions. Okay, one is the translational speed or translational motion. That means the ball, right, is translating, right, is translating. At the same time, this ball is rotating also. So if you combine these two motion, right, it will give you the rolling motion. Okay, it will describe the rolling motion for you. If we look at the next slide, which is this slide, it will be clearer. So pure translation, that means the motion that is moving only, okay, without rotation. Then pure rotation, because it's rotating, right? The rolling motion will be the combination of the vectors. Okay, as you can see, you see point 2, point 2. Translation, this point is going to the right, correct? But because of rotation, it's rotating clockwise. This point at the instant is going upwards, okay, it's moving upward. That's why you combine together, right? The vectors you add together is gonna be at a 45 degrees to the top right. Okay, it's actually combining, adding these two vectors together. Same thing for point 3. Point 3, translation is moving to the right. For rotation, right, because it's going like that, at this point it's also going to the right. What happens when you add it? It will be a longer vector. Okay, so this point, the top point here, when you look at the rolling motion, right, it will rotate very fast in the direction. Okay, you'll move very fast in the direction because it's actually two vectors pointing to the right, then you add them up together. Okay, same for point 4. And then you see point 1, which is the point of contact, right? Point of contact. This whole ball is moving to the right. That's why the vector points to the right. But for rotation, right, you're rotating clockwise. At this point, the rotation makes it point to the left. Okay, point 1 is actually going to the left. So what happens when you add them up together? It will become 0. Okay, so for rolling motion, it's as if this point is not moving at all. Okay, 0 velocity. Okay, so coming to equations, consider rotation about the contact point P. So now, by now you should know that rolling motion, a cylinder that is rolling like that, it is a rotation about this point P. So it's like the whole object, right, rotating around this point P for that particular instant only. But if you want to do analysis, right, at that instant, this whole thing is rotating about this point P. Okay. So kinetic energy is half I omega square. Remember, for something that rotates, is half I omega square. It's like a half mv square. But now we are looking at rotation, so it's half I omega square. And this is with respect to this point P. So you imagine a cylinder rotating about this point P. Okay, the whole thing rotate about it. That's why half I omega square, but the I, right, is with respect to point P. So this IP, right, remember, for cylinder, we already know what is the I for the cm. Then, remember what we need to do if the axis is not right at the cm, parallel axis theorem, right? So you will get this term coming out here. The original one plus your md square. In this case, the d is just the r, right, which is the radius. So IP will be equals to this expression over here. So if you go and expand this out, right, the whole thing will look something like that. Okay, which is a very nice equation. You have two terms. So kinetic energy equals to half I omega square with respect to the cm. That means you treat it as the cylinder rotating about its own center, about its own center of mass, plus also the whole thing that is translating to the right. Okay, half mv squared. So you see these two terms here, it's just saying the total kinetic energy is the kinetic energy from the rotation plus the kinetic energy from the translation. Okay, so you just add that two up together, that will be the total energy. Michael asked, what's I? That one we have learned in the previous topic is the moment of inertia. Okay, I is the moment of inertia. It's analogous to the mass, but when you study angles, right? When you study angles, sorry, not angles, when we study angular motion, there will be this I appearing, is the moment of inertia. Okay, so that's the one that we are talking about. Okay, yeah, then we continue. So now we come to sphere on an incline. So if you have an incline here and you put a sphere on top, what will happen? You all should know lah. So the sphere will roll down, right? It will roll down. So this is a rolling motion. Accelerated rolling motion is possible only if a frictional force is present. That means this contact point, the sphere and the slope, right? It needs to have friction, okay, so that the ball will start rolling. Imagine you put a ball, right, and then it has no friction. What will happen? The ball will just slide down, right? Slide down without rolling. So friction actually plays a part. You need to have friction for rolling motion to occur. So that's why now we are starting rolling without slipping. Okay, that's why frictional force needs to be present. No loss of mechanical energy because the contact point is at rest at any instant. Remember, when we say loss of mechanical energy so far, usually is due to resistive forces, right? Like friction. If you push a box across a surface, mechanical energy will be lost because there's friction present, right? Take away the energy, convert to heat. That's why loss of mechanical energy. But for rolling motion, you roll down and incline, but there's no friction. So no friction means you won't take away any energy, right? So in the ideal case of rolling, there will be no loss of mechanical energy. In other words, if something rolls down like that, the kinetic energy, which is the part coming from rotation plus translation, that's the kinetic energy, right, total, must be equals to the mgh. Mgh, remember what is it? Is our potential energy. So this whole mgh, right, is starting from here. It loses the potential energy. At this point, right, it must all be converted to your kinetic energy. Okay, for a perfect rolling motion without any friction, without any sliding involved. Okay, so the same previous equation, if you want to make it even simpler, you convert this VCM equals to R omega. Okay, because we already know VCM equals to R omega. So for here, right, they change this omega into VCM. So the omega will disappear. Okay, in that manner, you are going to get this. Basically, from here to here, right, it's just changing the omega to VCM and R. Okay, then from here, you make VCM the subject. This will be the expression for the velocity of the center of mass. Okay, this is the velocity of the center of mass. So you can see this velocity, right, at the bottom here, after going down a height h, right, the VCM at this point, it is determined by the height, obviously. So if you fall from roll down from a greater height, VCM will be larger, right, at the bottom point. That's why it's also affected by h. You can also see that it's affected by things like the I and the R. Okay, this is the moment of inertia. Okay, the higher the moment of inertia, that means higher resistance, right, is going to give you a lower VCM. You can see it's in the denominator, right? Okay, so the higher ICM going to give you lower VCM because more resistance. So we have found the VCM, right? How do we find the ACM, which is the acceleration of the center of mass? So actually got two methods. First method is the energy method. So we already know V equals to this expression, right? And then for a sphere, your moment of inertia is 2/5 mr squared. So to find acceleration, you use this kinematic equation here. Okay, kinematic equation. This is your v square equals to u square plus 2as. V square equals to u square plus 2as. U square is 0 because you start from rest, right? So this is your 2as. And then this distance, right? You can convert it to h and theta. You convert it to something with h and theta. This h, right, will disappear, okay? Because originally you already have a h here. You will realize if you convert and sub inside, right, this h will disappear. Then you are going to end up with an expression like this. ACM equals to 5/7 g sine theta. Okay, so the acceleration ACM, right? That means at this point here, at the bottom point, what is the acceleration of the CM? It has got nothing to do with the height. You realize? Okay, only the angle will affect the acceleration. The height will not affect the acceleration. Okay, so that's one method. You can also use the dynamics method. So you see, different methods can achieve the same thing, but maybe more effort. Okay, maybe more effort. So for dynamics, which is using forces, what you need to do, of course, first thing, draw a free body diagram. You always have mg pointing down. And then because of mg pointing down, you have mg sine theta here, mg cosine theta here, quite standard already. And then this thing is touching a surface, right? So there will be a normal contact force. And then for our rolling without slipping, there must be a friction here. Okay, there must be a friction here so that you will roll and then not slide. So the friction is acting in this manner, in the opposite direction. From here, right, you will go and take summation of forces in the both direction, x and y direction. For the x direction, which is along the slope, you have mg sine theta. From here, you also have f. Okay, so you take this minus this equals to ma. This part is not 0, it's ma because there is actually an acceleration which we are trying to calculate. Okay, so that's one of the equation. The other one in the other direction, you have n. You also have mg cosine theta, right? And then this thing is not moving in this direction, not moving in the y direction. That's why right hand side equals to 0. Okay, so we have these two equations ready. And then we can use other concepts to replace some of these terms inside. So we know tau, which is torque. This is our F times R. Remember, this thing is rotating. There is some torque to it. So torque is the force times perpendicular distance, right? The force that is trying to rotate it, to get this thing rotate, is actually the friction. Okay, can you see? This friction, right, is acting to make this thing rotate. So your torque will be your F times the perpendicular distance, which is your radius. Okay, so torque equals to I alpha, just like F equals to ma, but for circular motion, torque equals to I alpha. And alpha, we know we can change to ACM using this, because just now we saw that ACM equals to R alpha, right? So from here, you can remove the alpha by substituting this inside. So this whole thing will change. The alpha will get removed. ACM will start to appear, of course, along with R. And then you go and solve it. Your F, right, will be equals to 2/5 M ACM. Okay? So why do we want to get F? We get F so that we can put it back here in the first equation. Okay, so first equation, right? Then the F you change to this expression. Then from here, you make ACM the subject, and then you will get 5/7 G sine theta. You're going to get the same thing. If you refer to the previous slide, this is exactly the same. Okay, so this is how we get the ACM using two different methods. Okay, so that's rolling motion without slipping. So here are some questions that we can think of. What if theta is increased so that this friction, right, is greater than your mu Sn? Remember, mu Sn is the friction, right? What if the friction, what if theta is increased such that this thing, right, is greater than mu Sn? So this IE, this part here, right, is just rewriting the whole statement on top. Okay, it will be tangent theta bigger than 7/2 mu S. In other words, you can imagine, so now the incline is like that, right? The ball is rolling down. So if you go and increase the incline, then the ball will roll down even faster, right? But you, at the same time, you will also overcome the friction already. So other than rolling, right, this thing will also slide down. Okay, slide and roll at the same time. You will slide and roll. The velocity and angular velocity going to increase. But at that point, right, VCM will not be equals to R omega. They will not be related in that manner already, because we came out with this equation, right, with the assumption that the point of contact is not moving. Okay, but when something is sliding down, the point of contact is moving already. So this equation will not be applicable. Okay. Then on the other extreme end, what happens when theta tends to 0? That means this whole slope, become no angle. Okay, just a flat ground. Will F become 0? The answer is yes. There will not be any friction anymore. Okay, because you are going on a flat ground. So if friction equals to 0 and point of contact does not move, why does a rolling ball, say a basketball, ultimately stop? So imagine something rolling, right? Then the slope becomes 0. The rolling object, technically, it will continue to roll, right? And then it wouldn't stop because there is no friction trying to stop it, right? But in real life, there will be other resistive forces, okay, such as air resistance. Air resistance will try to stop the ball. And then also there's this thing called the rolling friction due to imperfections along the ground and also the ball. So just a very brief idea of what rolling friction is, because you guys are engineers, right? So this thing is what you are going to see now. Okay, so rolling friction, I'm not going to read this out, okay? Basically, what is rolling friction? The ideal case, right, is you have an ideal ball, very perfect one, on a very flat surface. But in real life, when a ball rolls down, right, the contact, even the ground, right, there's going to be some bumps. Okay, there's going to be some small bumps. So these bumps, right, will try to slow down and take energy away. Okay, we'll try to take energy away from the rolling motion. It also applies to, let's say, tires, car tire, bicycle tire, rolling also. The tire itself, right, is also not perfectly round. If you cycle, you realize if you never pump your tires enough, the tire will be flat, right? The tire will be flat, then the point of contact, right, it does not roll very smoothly. There will be a lot of rolling friction. Okay, there will be a lot of rolling friction. It will keep having a lot of this kind of bumps, okay, interacting together, the tire and then the ground. Okay, so if you want to cycle more easily, you reduce the rolling friction by pumping, increasing the pressure until the max. Of course, not to the point where it will burst. Same thing for vehicles. Of course, vehicles you drive, right, you just step the pedal only, you cannot feel. But actually, if you never pump your tires, right, it's going to take out a lot of fuel. Okay, because you need a lot more energy to roll the same tire. It always has a lot of rolling friction. So we try to reduce that by pumping the tires frequently so that you can maintain your fuel efficiency. Okay, so that's rolling friction. So racing down incline, a ball rolls without sliding down. A ball rolls without sliding down incline A. So A is this figure where you have this ball, the one that we have been going through, a sphere, right, rolling down the incline. Then just now we have calculated that the acceleration of this is actually 5/7 g sine theta. Right, then you compare this B. A box slides down a frictionless incline B. Also at the start of the module, we have been talking a lot about this, right? This box sliding down the incline. And then in this case, we imagine it's frictionless, so it will just really slide down. Okay, A and B have same dimensions, it's the same slope, which gets to the bottom first. Of course, the answer is already here. So let me explain. ACM, we have calculated, is 5/7 g sine theta for the rolling motion. Remember our box. We always draw the free body diagram, right? What is the acceleration? We always know that this direction pointing down is the mg sine theta, right? So the acceleration is just g sine theta. Okay, you go and compare the acceleration of this box and the acceleration of the sphere. You see that the acceleration of the sphere is lower than the box, right? Not very intuitive. You will think that ball can roll down faster, but if you have a box rolling down, sliding down an incline, frictionless incline, right, it's gonna accelerate much faster. Okay, why? They have same height, but why? Because this object, same potential energy, right? Same height, but the potential energy not only has to go into moving the ball down, it also has to go into rotating the ball. Okay, so the energy is split up into rolling and translation, rolling and the translating part, right? So the translation part will end up having less energy. For this case, right, the mgh, the potential energy, all go into the translation. Nothing needs to rotate. That's why it will have higher energy. Okay, higher translational energy. Okay, then another example of raising down incline. Three objects of uniform density. One is a solid sphere, one a solid cylinder, and then also a hollow cylinder. So these three, they are placed at the same line, and then they are all released from rest. You try to want to see which one goes down at the bottom first, which one reach the bottom first. And then also we assume that there is no slipping, okay, which is what we have been studying up to now. Which object reach the bottom first? So if you look at this equation, you compare VCM, right? The top you realize will be the same because they start from the same height. Radius actually same also, but the I will be different. Okay, this I is the moment of inertia. It's like the mass, okay, resistance like that. So the higher the resistance, the higher the moment inertia, the slower it will go. That means it will take the longest to reach the bottom. Okay, so you have to go and compare your I cylinder, I sphere, and then also the I hollow cylinder. From here, you can straight away see, okay, the hollow cylinder has the highest I amongst them. Okay, it's the highest I. This I cylinder is just half mr square, but this one is half m, not just one square, r square, is both the r square. It's a higher value. Okay, followed by the cylinder, which is half. This 2/5 is smaller than half. Okay, so you roughly already know the ranking. But you can also roughly appreciate why. Okay, remember I say for hollow components, right, all the mass, they are pushed to the sides. So when the masses, they are pushed to the sides, right, you will get a lot of resistance. Very hard to turn something that is further from the point of rotation, remember? So hollow one, it will take more energy to try to get it rotate. That's why it's going to reach the bottom the last. Okay, so far with rolling without slipping. Okay, everything okay? Any questions? Rolling without slipping? Then we go into if you got questions, you can just type out. Later when I check, I can answer. Okay, for now we go into rolling with slipping. That means this object, right? It not just roll on the surface, it also slides as it rolls. Okay, at the same time, it's also sliding. So that's the key part. Okay, down here at the surface here, this point of contact, right, is no longer zero velocity. Okay, so when things slide and roll at the same time, right, V will not equals to R omega. Okay, there will be kinetic friction acting on this object. So we can imagine the sliding part, right, is like a box sliding across a surface. Okay, it's like a box sliding across a surface. When that happens, it's not static friction anymore. It's a kinetic friction that is taking away the energy, right? Because it is already in motion, sliding motion. So there are mainly two scenarios for rolling with slipping. The first one is for VCM greater than R omega. What does this mean? That means this VCM is the translational speed of this ball, right? It's the translational speed. That means it is moving forward faster than it is supposed to rotate. Okay? I say again. So VCM is the translational velocity. So if VCM bigger than R omega, right? So normally if there's no sliding, V equals to R omega, correct? But this case, it is bigger than R omega. So it is actually translating faster than it should rotate. Okay? Translating faster than it should rotate. These forces will look like this. Okay? Down here, because it's moving to the right much faster than it should rotate, it is sliding on the ground, okay, at that moment. So there will be this friction pointing backwards, pointing to the left. Okay, there will be friction pointing to the left. So this diagram here is rolling here with omega. You can write out two equations. One is your MA, V dv cm over dt, this is your acceleration, right? Translational acceleration. Okay, that means the motion of the ball, translational motion of the ball, MA equals to minus F. So this friction that is acting in the opposite direction is trying to slow the whole ball down. Okay, there is friction trying to slow the whole ball down. Okay, so this is like looking at the macro scale lah. Okay, it's moving to the right, there's friction pointing to the left, it's going to get slowed down. Then for rotation, right, the equation will be like this. I alpha, d omega over dt is your alpha. So I alpha equals to your top. So the top here is your force times radius. Okay, force times perpendicular distance. Okay, because there's friction involved, right? So this force here is trying to get this thing to rotate faster. There is a top. That's why you see when this thing is sliding so much to the right, the rotation haven't catch up, right? There will be this mechanism here, so-called mechanism, such that it will decrease this VCM, and then this F is acting, right? It will increase the omega. Okay, VCM will start to decrease. That means the ball will slow down, translational wise, but then it will start to spin faster and faster. Until when? Until V equals to R omega. Okay, so it slows down, but it starts to spin more and more until this condition is met. When VCM equals to R omega, right, that means it's rolling without slipping. You realize this F here, right, will disappear. Okay, there will not be this force anymore. That's why it will stop rolling faster. Okay, this part everyone can understand. So in real life scenarios, right, how will this thing happen? If you all play billiard or pool, right, if you take the stick and hit at the middle of the ball, if you hit at the middle of the ball very hard, okay, that's what will happen first. You may not be able to observe, but the ball will get jerked in front first without rolling. Okay, after a certain distance, then it will start to roll. Right, so the ball will travel like this first, then you will start to roll and roll and roll. Okay, so that's what's going to happen. Then the other case, right? So that's one case. The other case, rolling with slipping, right, is the opposite case, actually. Just now V is greater, right? The other opposite case is now V is smaller than R omega. This ball, right, is going to the right, but it's rotating so much faster than it's supposed to move. It's rotating so much faster than it's supposed to translate. Okay, that means it's like rolling a lot more on the spot than it's supposed to go to the right. So if this happens, right, what are the forces involved? Okay, same thing, you look at this point P, something is going to slide there, right? So there will be some friction. But where is the friction pointing? Okay, the ground is here, it's moving to the right slowly, right? But this rotation is so fast that this point is like moving to the left. Can you see this point P is moving to the right, but the rotation is so fast that that point P, right, is moving to the left. It's moving to the left. So if the point P is moving to the left, what is the force? What is the friction force involved with the ground? The friction will be pointing to the right, correct? Because it's as if point P is sliding to the left at that moment. So friction points to the right. And this friction pointing to the right is important. It's important because it will give you these equations. So MA equals to F. You can see this whole system, right? This friction force is trying to speed this ball up. Okay, it's trying to increase VCM. It's trying to increase VCM. And then for the rotation equation, right, is your I alpha. This one is alpha. Alpha is angular acceleration. So I alpha equals to your top. And then in this case, the top will be minus FR. It's rotating like this, right, clockwise. But the top that's coming from this F is actually in the opposite direction from the rotation. Can you see? It's rotating like this, clockwise. But this F, right, this friction force will give a counterclockwise torque. Anti-direction. That's why there's a negative sign here. Okay, so what happens if the equations look like this? It basically means VCM will increase because you have positive acceleration, right? So the ball will start to translate faster and faster. And then at the same time, omega will decrease. Okay, and then same thing, this will stop when V equals to R omega, when there is no more slipping. So when something is slipping and rolling at the same time, right, this will occur. Okay, friction will occur and then put things back in place. Okay, and then put things back in place. So again, same thing with the billiard or the pool, right? This is like you taking a stick, right, and then hit the top of the ball. Okay, very fast. That means you set the ball. You imagine the ball is here, right? If you hit at the top, right, very hard, you are going to set the ball into a lot of rotational motion rather than a translation, right? You set it into so much rotational motion such that it's rotating so fast. Okay, this is what is going to happen. So after a while, it will speed up the ball. The rotation on the spot, right, will speed up the billiard ball, and then that's why the ball will speed up. Okay, until V equals to R omega. Until V equals to R omega. Okay. I mean, there are many other real life examples lah. So if you go and let's say if you go and roll a marble or ball or soccer ball backwards, okay, you throw forward but you rotate it in the anti direction, you will go and notice what will happen. Okay, if you rotate it so much that you have a lot of rotational energy backwards, right, you'll realize the ball after traveling forward, you will come back. Okay, so that is rolling with slipping. And then when will it stop? It will only stop when it balances out itself. Okay, V equals to R omega, then that will stop already. Okay, so let's go into an example. A uniform sphere rests initially on a level floor, like this. An impulse delivered horizontally at its center gives it a starting speed of 1 meters per second and causes it to skid and roll on the floor. After 0.5 seconds, it stops skidding and turn to pure rolling. Calculate the coefficient of sliding friction due to contact with the floor. So they are asking you to find a mu k, asking you to find the friction coefficient, right? So V naught equals to 1 meters per second. Skidding changed into rolling in 0.5 seconds. So they tell you in the first 0.5 seconds, it's actually rolling with sliding. After that, it changes to normal rolling. Okay, so there are two motions, rotation about cm and translation of cm. This is for rolling, right? So this is the free body diagram for the start. So it starts with VCM equals to 1 meters per second. But at this point in time, right, it is also sliding. So if something slides, you're going to get a friction in the opposite direction, right? You're going to get friction in the opposite direction. Of course, mg will always be there. Like, if you want to draw forces, draw everything, mg will be there. Okay, so during skidding, VCM is not equals to R omega. So for translational motion, we talk about translation first. This is the equation that's involved. This is your V equals to U plus AT. Okay, this is your kinematic equation. V naught is the same as U lah. This is your initial velocity. Okay, this whole chunk here, mu k mg over m. This is your acceleration. Okay, mu k mg, this is your friction force down here. This is your friction force. Divide by m. Force divided by mass gives you the acceleration. Okay, so the whole thing is your acceleration. And it's in the opposite direction. That's why you get a minus sign. Okay, essentially it's just V equals to U plus AT. Okay, then the mass cancel out, it'll look like this. Then you go and look at the rotational motion. For rotation, alpha equals to tau over I. This is your torque, this is your moment of inertia. Okay, so the torque, what is the torque involved for the rotation? Is your force times perpendicular distance. Okay, force times perpendicular distance. Is this force, right, this friction force, right, that is setting the rotation. Okay, it's setting up the rotation, increasing the rotational speed. Okay, that is the torque. So torque equals to F times R divided by your moment of inertia. Moment of inertia is, it depends on the shape. Okay, in this case, it's 2/5 mr squared. Then it will give you this. This is your omega equals to omega naught plus alpha t, which is your V equals to U plus AT equivalent. Basically, down here you get alpha, right? Down here, this omega equals to omega naught plus AT. You just sub this alpha inside here. Okay? Omega naught is 0 because at the start, it's not rolling, right? So you only have omega equals to alpha t. That's why it's just this expression, and you put a t behind. Okay, so you have two equations now. One is V, one is your omega. Why you find that? Because you know the criteria for rolling without slipping is V equals to R omega. Okay, they tell you after 0.5 seconds, it becomes V equals to R omega, right? So if you go and compare, you put V to this expression here equals to R omega. So you write out exactly what V equals to R omega is. Then this T, right, you see there's this T inside the equation. This is your time. It takes 0.5 seconds for this to happen. That's why T, you just sub 0.5. Inside here, you just solve for what you need to find, okay? Which is mu k in this case. Okay, so you will find the answer mu k. Okay, any questions? Then after that, a supplementary question, which you all can go and read on your own for this part. Okay. Mu k is dimensionless, right? Yeah, it is. It's a coefficient. It's a friction coefficient, okay? So, yep. Any more questions for this one? If not, then we can continue to the next topic, which is 15. Okay, so I'll stop share this one and then share the new one. Okay, so now we move on to topic 15, angular momentum. We've studied linear momentum, right? So now we move on to this thing called angular momentum. So for now, we have to revise this thing called a vector product. Okay, we revised dot product before, right? So there's also this cross product, which is different, different from dot product. So given two vectors A and B, the vector product is a vector C. So cross product, right, you write it something like that. C equals to A cross B. And then for cross product, it is your AB sine theta. Remember your dot is cosine. Cross product, it is sine. Okay, sine. It is equal to the area of parallelogram formed by the vectors. So imagine you have A here, you have B here, right? If you imagine a parallelogram formed by this A and B, this magnitude, right, is actually equals to the area of that. Okay, another thing is the direction of C is perpendicular to the plane formed by A and B and is given by the right hand rule. So for here, right, if you do A cross B, you just use your fingers, right? You sort of like rotate A towards B. Okay, rotate A towards B. This is your right hand rule. Then wherever your thumb is pointing, right, that is the direction of the resultant vector. Okay, so in this case, if you put A cross B like this, right, it's pointing upwards, thumb is pointing upwards. That's why resultant vector pointing upwards. So from here, right, if you do a B cross A, your whole hand gonna tilt, right? Just now A cross B like this, but B is here. So if you do a B cross A, right, your whole hand will tilt around. Then you realize, oh, actually the resultant is pointing downwards. Okay, so A cross B is not the same as B cross A. If the order of the vectors are changed, the sign of the cross product changes. Okay, this one I just talked about it. I just explained why. Okay, the direction will be different. If A is parallel to B, then A cross B equals to 0. Why? Because it's sine theta, right? If parallel means theta equals to 0. And sine 0 is just 0. So if it's parallel, the whole thing gonna be 0. If A is perpendicular to B, that will give you the maximum magnitude. Perpendicular means angle equals to 90. And we know sine 90 gives us the maximum. Okay, sine 90 is 1, and that's the maximum. Vector product obeys the distributive law, which means A cross a bracket like this, right? With B plus C inside, it will be A cross B, you do like this, plus A cross C. So vector product, right, is like your normal multiplication. In this case, for this particular one. So if you look at unit vectors and the cross products, right, it will look like this. If you cross something with itself, because it's in the same direction, right? So it will end up as 0. But if you cross with another unit vector, you can see that they are always nicely in 90 degrees, correct? They are always nicely in 90 degrees. So the resultant, right, will always be in the third direction in some form. Okay, there might be minus sign involved. Okay, so if you do a I cross J, that means you put your fingers, right? You curl your fingers from I to J like this, you'll realize it will be K, okay, pointing upwards. And the rest is also the same. Just follow the same right hand rule. Okay, so why we study cross product? Because we need to understand cross product to understand this topic. Remember that torque of a force was earlier defined as torque equals to force times length. Okay, we also just did it just now, right? Torque equals to force times your perpendicular distance. Actually, that one is what? RF sine theta, which means torque is also just equals to your R cross F. Okay, you R cross F, you're going to get sine theta involved, right? So actually, the definition of torque is also R cross F. Not F cross R, is R cross F. Direction of vector is normal to the plane formed by R and F. Okay, so if you have your radius here and then the force you apply at a weird direction, right? You're going to form some angle. So the torque, okay, which is pointing in a totally different direction, is your R cross F. And then because you see your vector R is here, right? If you go and use your right hand rule, it will rotate from R towards F. Okay, R first, then F. That's why you use your right hand rule, right? You'll realize the resultant vector is pointing upwards. So the torque is pointing upwards. Now we come to angular momentum. Angular momentum. Remember our linear momentum is equals to mass times velocity. Right? So now we come to angular momentum, actually about the same. Okay. The instantaneous angular momentum, sometimes you write as L, sometimes write as H, of a particle relative to the origin O is defined by the cross product of the instantaneous vector position, that is your R, and instantaneous linear momentum. So angular momentum, right, is just take the vector position R cross the linear momentum. Okay, so R cross P will give you an angular momentum. And of course, the direction is based on the cross product. Okay. Anyway, so for this particular case, why is the resultant pointing top? Because R first, right? If you draw the whole vector out, okay, extend all the way, you'll realize you want to do R cross P, right? Your fingers will rotate from R towards P. Okay, R towards P. That's why the resultant, which is the angular momentum, is pointing upwards. Does a particle moving along a straight line have any angular momentum? It's a concept question. Okay, remember we say angular momentum is R cross your P, right? R cross your linear momentum. So if a particle is moving along one straight line, like this, will it have any angular momentum? Actually, the answer is yes and no, depends on your choice of origin. So the choice of origin is important here. If you see, if your origin is here, right, If your origin is here, R will be like this, from where the origin is to the object. And also in this case, the object is still continuing in the same direction. Okay, so if you do a R cross your MV, you're gonna get 0. So if you choose the origin to be here, right, there will not be angular momentum. Okay? But if you choose the origin somewhere else, let's say a distance away, and then now R is from this origin to the object, right? The object is moving to the right. So in this case, if you do a R cross your MV, you're going to get a value that will be some angular momentum. Okay, and logically, it will make sense, right? You ask yourself, if this is the origin, if you are the origin, something is going away from you. It's not even from your point of view, it's not even rotating. Okay, it's not even rotating anywhere. You will just see the point moving away. When something is not rotating, there will not be any angular things going on, right? That's why it will be 0. But if the choice of origin is away from it, you can see at this instant, this thing is almost like it's rotating about the point, right? It's going to the right, but the point is here. So there's some sort of rotation about the origin. So if you have rotational stuff going on, there will be angular stuff going on. Okay, in this case, it's your angular momentum. Okay, makes sense, right? Then now it's come to equations. So what is the angular momentum equations? Okay, so briefly, this is how we come up with it. So we know that torque equals to R cross F. Just now we talk about it, R cross F. This F, you can also change to dP over dt. Remember your linear momentum, the impulse portion, F equals to dP over dt. Okay, maybe you will remember it as your linear momentum equals to force times change in time. Okay, which is the same thing you see. This P, right, is actually equals to F and T. Okay, so this is one equation. The other one is if you go and differentiate your angular momentum, right? Angular momentum, you can also change it to R cross P. Okay, and then if you differentiate a cross product, actually it's going to be like that. Okay, R cross dP over dt plus dr over dt cross P. So this part, right, this dr over dt cross P is actually this dr over dt. You can also change to v because you know a differentiate your position vector, you're going to get velocity. And then momentum is your mv. So something in the same direction, when they cross each other, right, you see there's a v here, there's also a v here. If you cross each other, it's going to be 0. So we know this whole term here, right, this dr over dt cross p is actually 0. That means this whole equation here, it will simplify to just r cross dp over dt, like this. Okay, and that will give you your tau equals to dl over dt. Okay, because you compare to the first equation. The tau equals to dl over dt. You can see the similarity between angular momentum and linear momentum. The linear one, you have F equals to dP over dt. The angular one, you have tau equals to dL over dt. This is the force equivalent, right? This is just angular momentum. Okay, so now you just change it to the angular counterparts, right? The equation is true again. Okay, just like any other topics. Okay, so this is the equation. The torque acting on a particle is equal to the time rate of change of the particle's angular momentum. Okay, torque equals to dL over dt. The time rate of change of the total angular momentum of the system about some origin in the inertial frame equals the net external torque acting on the system about the origin. This statement just means that if you have many torques acting or many forces acting, you will just sum them up together. Like what we will be doing, what we have been doing for linear momentum also. Okay, same thing, this is just a summation. If you realize the formula looks almost the same, you see the torque here, summation of torque equals to dl over dt. DOT is total, so total angular momentum over dt. So remember when you study linear momentum, there's also something called the impulse, right? Impulse is the change in momentum. Remember, impulse is the change in momentum. So angular impulse, also the same thing. Just that if you put an angular in front, right, means it's the change in angular momentum. Normal impulse is change in linear momentum, normal momentum, right? The angular means change in angular momentum. Okay, basically this one is just saying tau dt equals to change in angular momentum. Exactly same as a linear counterpart also. Linear counterpart, it will be f dt equals to change in linear momentum. Okay, same thing. So now we come to rotating rigid objects. We consider a rotation of rigid object about some point O. That means this object is rotating, okay, about this point O. What is the angular momentum of this object? It will be your R times your linear momentum. Okay, R is this one from the origin to the point. Linear momentum of this particular point, right, is your mv. All right, angular momentum equals to R times linear momentum. It was from the previous few slides. L equals to R times P, right? That's why you get R times mv. So if you rewrite it, you know V equals to R omega because this is just rotation, right? So basically you want to remove this V, write it in terms of omega. Okay, actually it means the same thing. So you're going to get mr square omega. This is your angular momentum for one particle on this object. For the whole object, right, you just sum the whole thing. Just sum up the whole thing. Which is also the same thing. Mr square omega is the same formula you can see, right? And then you realize something special here. This mr square, right? Remember what was it? It was the moment of inertia that we have been studying. Because moment of inertia equals to mr square, right? So you can rewrite this whole thing to become just I omega. Okay, so angular momentum equals to I omega. And down here, by looking at this equation, do you find some similarity with the linear counterpart? Linear momentum equals to mass times velocity, right? Now we have angular momentum equals to moment of inertia times angular velocity. Basically, same thing again. Whatever linear stuff, right, you change to the angular quantity, the equation again is true. Okay, so many similar concepts. That's why if you are good at linear part, right, usually the first part of the course, the angular part should be okay one for most parts of it. Okay, until maybe mechanics of machine, then get confusing, slightly confusing, okay. But this rotation angular part, right, is almost exactly the same kind of understanding. Okay, then we continue from that same equation. Your L equals to I omega. If you differentiate it, you're going to get A alpha. So you see, you come back to the same equation. dl over dt, that is your torque, right? And then if you differentiate this omega with respect to time, it will change to alpha. So in the end, you are going to get torque equals to I alpha. Come back to the same formula. So everything is just related. Okay, let's look at one example. A rigid rod of mass M and length L is pivoted without friction. The two particles of masses M1 and M2 are connected to its ends. The combination rotates in a vertical plane with an angular speed omega. Find the expression for the magnitude of angular momentum and acceleration of the system. So basically, you have this rod here, and then you attach the masses at the end, and there will be some weight, right, pulling it down. So these forces will also set this thing into some rotation, and that's how you get this angular speed. They ask you to find the angular momentum and also find the acceleration of this system. So you want to find the total torque that's associated with this whole object. It will be the torque due to your mass 1 plus the torque due to your mass 2. Okay, so the free body diagram will have force pointing downwards due to gravity, which is your mg, right? So torque will just be this force times the perpendicular distance to the pivot. Okay, so the perpendicular distance is this. Okay, for 1, the perpendicular distance is this distance. For 2, the perpendicular distance is this distance, basically to the y-axis. The distance from y-axis to the particular object, right? That will be the perpendicular distance. Okay, so torque 1, you will get your mass, the force due to this mass, which is m1g times that distance. Okay, it's L/2 cosine theta. Okay, then tau 2 is actually the same thing. Just that they are giving torques in different direction, right? One is trying to rotate counterclockwise, one is trying to rotate clockwise. So definitely one will have a minus sign. Okay. Then your I, which is the moment of inertia, is based on the entire object, which is made up of the rod itself and then also the two masses. So rotation about the cm of a rod is given by 1/12 ml square. Then you have to add on the moment of inertia due to m1 and m2. Okay, moment of inertia is mr square, right? That's why you get m. Your r is actually your L/2 square. Same thing for m2. Okay, so you have something for tau 1, you have something for tau 2, you have something for I, you're left with alpha. So if you combine all these together, right, and make alpha the subject, you will get this expression. I mean, of course, if you have numbers, you just put in, then you will get a value for that. What's the angular acceleration? Okay, then how to find the angular momentum? Angular momentum is your I times omega. Okay, I times omega. So you just take this I, multiply by your omega. Okay. Okay, so that is angular momentum. And then same thing, same as your linear momentum, we also have this thing called the conservation of angular momentum. And if you are guessing, you could probably be correct. So angular momentum also must be conserved, just like linear momentum and just like energy. Okay, so total angular momentum is constant if resultant external torque is 0. So if you have no forces or no torque on the system, right, the angular momentum shouldn't change. Okay, so it should maintain constant. So if you write it out, right, it's going to be I omega for the initial phase must be equals to I omega for the final phase, which means angular momentum at the start must be equals to angular momentum at the end. But this thing must take note because we are talking about angular momentum, right? It is only valid for rotation about fixed axis. Remember just now, we say the different axes will give us different angular momentum. If you do this conservation of angular momentum, the axis, right, must maintain the same. Cannot anyhow go and change the axis. Because if you change axis, right, it means the distance that r, right, will change. Then whole thing will change already. Okay, it's different. So if the axis is the same, right, the rotational axis, then this I omega at the start will equals to I omega at the end. Okay, let's take a look at this example. A spinning scientist. So a scientist stands at the center of a turntable. That means this thing, imagine he stands on this thing, it can rotate. Okay. He stands on top of it and then he carries 5 kg dumbbell in each hand. I is moment inertia. He has a moment inertia of 3 with arms extended and moment inertia 2.2 when he pulls the dumbbell to his stomach. So his body himself, right? Let's not talk about the dumbbell first. When he stretch out his arms, he will have a moment inertia of 3. When he put his arms to the body, he will have a less moment inertia. Okay, and that's given to you. So what's given to you is also the R1 and R2. Okay, so basically R1 is he's spinning, right? So the dumbbell to the center of rotation, that is your R1. Okay, and that's 1 meter. Then after that, when he's spinning, he pulls the dumbbell closer to him. So the dumbbell to his center rotation, right, will be reduced to 0.2. So they tell you if the period of revolution is initially 2 seconds, it means T1 equals to 2 seconds, what is the final angular velocity? Compare initial and final kinetic energies and explain why it's different. So this question is, he is just spinning, right? Imagine he start this problem, he is on this turntable, he's already rotating himself with the dumbbell outside. Right? So there's an angular momentum to the start of this, this thing already. Okay, then later, he never add any torque, correct? No one go and push him or what. He just bring the thing closer to his body only. So the angular momentum at the start must be equal to the angular momentum at the end. So we need to go and calculate what is the total moment inertia first. Okay, for the start and the end. The moment inertia for the start will be his body himself. The question tell you is 3, right? You must add the 2 dumbbells also. Okay, that is 2 times your mr square. That's why it's the body plus 2 dumbbells. That will be the total moment of inertia. Okay, then for omega 1, which is your angular velocity at the start, they tell you the T is 2, right? Period of revolution. So you convert to angular velocity, you're going to get 3.14 radians per second. You get it in this form because you want to apply I omega. Okay, you cannot use T itself, it's useless. So you need to convert it by using 2 pi over T to get the omega. After that, you can apply I omega equals to I omega. Okay, then the second part of the question asks us to compare the kinetic energy, right? So you can also do now first, later you can compare. So what is your kinetic energy for rotation? It is your half I omega square, right? You have your I, you also have your omega already. So you can find your kinetic energy at the start. Okay, so this is the starting scenario with the arms extended. Now when he's rotating, right, he's going to pull his arm in. Okay, what is the new moment inertia? They tell you the body with the hand inside is 2.2 plus the moment inertia of the 2 dumbbell also is your 2 times mr square. The r has been reduced by a lot, take note. Just now is 1, now is 0.2. So the moment inertia for this system, right, is going to become much smaller than just now. 13, now it's 2.6. With this info, you can apply your I omega at the start equals to I omega at the end. Okay, so you can find your omega at the end. Why? Because you know I1, you know I2. You also know your omega 1. So you can know when I changes, right, what will be your omega 2. Okay, so you can put in the values, you'll realize omega becomes 15.7 radians per second. Just now he only rotating at 3.14. Now he speed up a lot. He speed up to 15.7 radians per second. Doesn't look very intuitive, right? But this is what's going to happen. Because of conservation of angular momentum, if you have a lot of mass outside, right? You have a lot of mass outside, you have very high moment of inertia, you go and bring the mass closer to you, your moment of inertia decrease. And because of that, your angular momentum must be conserved, right? So you will have no choice but to increase your omega. You have to speed up a lot to compensate for that. Okay, and then in real life, you all got watch the Olympics or that, like what's that sport called? Figure skating. You know, like Kim Yuna, they will dance around, they will skate around the ice ring, right? And then there will be this point where they spin on the spot. You realize sometimes they start from slow spin, then they can speed up one. You know how they do it? No one is pushing them, you know. So this is the concept that they are using. Okay, when they start their spin on the spot, right, they will make sure more of their limbs, of course, one leg has to be on the ground. So the two arms and then the leg, right, they will put it furthest apart. Okay, and then they start the spin. Then they will slowly bring these arms and the legs, right, the other leg, closer to their body, the axis of rotation. When that happens, right, he or she will spin a lot faster. Okay, they are using this concept to spin them up. Nobody is pushing them. Okay, so that is from the conservation of angular momentum. Okay, if you want to test this thing on your own also can, like if you have a very nice swivel chair, can spin one, like you, if you have dumbbell at home. The heavier dumbbell you use, the more obvious the effect will be. You can go and do this thing. Okay, you take a two dumbbell, put at the furthest end, carry at the furthest end. Of course, it will be quite tiring. Then you spin yourself. Then you try to pull your dumbbell towards yourself. You will speed up definitely. The heavier the dumbbell, the more you will speed up. Okay, you all can go and try it. Okay, so that is part one of the question. Then the part two asks you to compare kinetic energy, right? Just now we already do K1. So same thing, the final state, you can also compute your K2. Use your new I2 and your omega 2 to find out K2. Okay, so you can see the kinetic energy when you rotate so fast, right, is so much higher than the one before that. Just now 64.2 only. After you pull in, right, you rotate so much faster, your kinetic energy increased by so much. So you see, the kinetic energy of the system, right, suddenly speed up by so much. But how can kinetic energy speed up, right, when you don't really see someone that pushing him or what? But actually the scientist, the person himself, right, he's actually doing work for this to occur. So the scientist, he has to do work to increase the energy of that system. In his frame, right, there are forces pulling the dumbbell outwards. If you spin something, things will want to go out, right? Imagine you are sitting on a chair, you spin your dumbbell wants to move out. But you apply inward force to pull the dumbbell towards yourself. Okay, it will be quite difficult, especially when you're spinning, because the faster you spin, right, the dumbbell want to go outwards. But at this time, right, you not only prevent it from going outwards, you are also pulling it to yourself, which is to the middle. So this a lot of work that you do, right? This applies energy to the system. That particular work you do applies energy to the system. Okay, so that's where this energy is coming from. Coming from you, you have to give the energy. Okay, another example. A star rotates with a period of 30 days around an axis through its center. After the star undergoes a supernova explosion, the stellar core, which had a radius of this amount, very huge, collapses into a neutron star of just 3 km radius. Determine the period of the rotation of the neutron star, which is after the explosion. Okay, so this is just a simple case of conservation of angular momentum. Okay, suddenly something that is big and then rotating suddenly becomes very small. So what is the new rotational speed? Right, it's from this I omega final equals to I omega initial. So moment of inertia is your 2/5 mr square. We assume they are spheres, right? 2/5 mr square. After that, also initial is 2/5 mr square. After that is also 2/5 mr square. So because we assume they are both spheres, but the radius, right, changed by a lot as written in the question. So if this radius changed by a lot, this period of rotation, or rather the rotational speed, will also change accordingly, okay, to this conservation of angular momentum. So if you use this to calculate, you will get the new period. Okay, you see a star that is so big, right? The rotation, the period is actually 30 days. But after that, it becomes very small, right? To go one round, you only need 0.23 seconds. Okay, because the radius changed by a lot. Okay, then one more example. I think should be the last example. Okay, a 2 kg disc traveling at 3 meters per second strikes a 1 kg stick of length 4 meter that is lying flat on a frictionless ice. Assume elastic collision and that the disc does not deviate from its original line of motion. Find the translational speed of the disc, translational speed of the stick, and also the angular speed of the stick, omega, after the collision. So you have this disc that's moving. Initially, this stick here, right, is not moving. After collision, this is what will happen. The stick will start to rotate, all right, and then also move to the right. Because something strike from the left, right, definitely you will also move to the right, but because it's strike at the side, all right, you will also start to rotate. And then they tell you after the collision, right, this never change direction, continue to travel in this direction. Okay, so that's the info given. So for this question, right, all the conservation laws will apply. The first one that will apply is your linear momentum. It must be conserved. Initial phase, right, only got this disc moving, so you are only going to have mv for the disc. After collision, the disc is still moving, so you have the mv for the disc. And then the stick, right, has also started moving. That's why you have your mv for the stick also. Okay, so that's our linear motion. For angular momentum, also must be conserved. Angular momentum, it depends on which axis we look at, right? So the most convenient for rotation, the axis, right, we'll just take it as the center of the rod. Okay, if you treat the axis as at the center of the rod, you compute your angular momentum from that, you are going to get like that. Your initial state, right, the rod is not moving, but you have the disc that's moving here. So what's the angular momentum of the disc? It will be your r times the linear momentum. Right, your distance times the linear momentum. Okay, then of course you better to stick to your conventions lah. This, with respect to the center of the rod, right, this rotation is clockwise, correct? So better follow lah, put minus. Clockwise usually means minus. Okay, then after that, after collision, your disc is still moving. So same thing, Just that now is the final state. You don't know the values lah for now. Then you also have another thing that is rotating, which is the rod, right? The stick. So the angular momentum for that is your I omega for the stick. Okay. Then down here, things are moving, right? You also can write conservation of energy. So kinetic energy at the start, there's only this moving, half mv square. After that, after collision, the D still moving, half mv square, plus the stick is also moving, that's why half mv square for the stick, plus the stick is rotating. Okay, that's why plus half I omega square. You must account for everything. So you see, if you write out all these, right, you will have three equations. Okay, so if you go and put the values inside, you see how many equations you have and how many unknowns you have. If your unknown equals to the number of equation, right, you know you confirm can solve. In this case, yeah, three equations, three unknown, right? But they ask for your Vs and your omega. The third unknown is your VDF. That means the velocity of the disc after collision. You can also find out that is not shown here. Okay. Any questions for this one? If don't have, then I will take a short break. Maybe we start again at 8:20. Okay. Okay. So those online one go and stay in the chat. Okay, I will mark attendance based on whoever is in the chat. Okay. So see you all again at 8:20. Okay, let's start topic 16 on static equilibrium. Okay, so anyway, static equilibrium, right? If you all have done or are doing mechanics, right, this will be quite okay for you lah. Could be even a revision. Maybe you all know more than this already. Okay, but I will just assume you all have no knowledge and then do from the start. Okay, static equilibrium is actually an important topic for engineers. Okay, so what is static equilibrium? So when a rigid body is at rest, that means it doesn't move at all. There's no translation, no rotation. We say that this object, right, this body is in static equilibrium. Static means no movement. Equilibrium means the forces all balance out. Okay, static equilibrium. So there will be two conditions to meet this equilibrium. One is net force on the body must be equals to zero. As you all know, when net force equals to zero, right, the object will not start to accelerate anywhere. If net force equals to zero, it will just stay in place, right? It's net force, it's not totally no force. So you can have a lot of forces pushing the object or pulling the object. As long as everything is cancel out, right, net force zero, then you fulfill the criteria. Okay, that will be your summation of F equals to zero. Okay, and then in each respective directions, also that must be true. The other criteria is your net torque about the axis, about any axis lah. Okay, must be equals to zero. If the net torque is zero, right, means the object will not start to rotate. Because if about any axis, there will be a torque, right? If there's a torque, confirm it will start rotating already. Okay, so net torque also must be zero. If that's fulfilled, then this thing is in static equilibrium. Okay, so let's look at these two scenarios. One is this: you have an object here. Let's say you apply force, different forces lah. Okay, one is force F at the side, the other one force F at the side. So these two got same magnitude, right? Pointing up. Then in the middle, you're going to apply 2F pointing down. That means 2 times the magnitude of F. Okay. So if you can look at this thing, you see whether the conditions are satisfied. So net force, whether is it zero, 2 pointing up, right? 2 separate F pointing upwards. Downwards, you have a 2F. Net force, is it zero? Yes, it is. Okay, so this object won't translate. Okay, then if you go and look at rotation, right? Go and look about this point. You have a F trying to rotate. This F trying to rotate anti-clockwise. The other F trying to rotate clockwise. This will cancel out, right? The one below is acting in the middle. So it's not going to cause any rotation, right? So the net torque about any axis is also zero. So this first object that we're looking at, right, it is in equilibrium. Okay. Then the next one on the right, you have a F on the left pointing up, and then F on the right pointing down. So first condition satisfied, upward force cancel downward force. But if you look at torques, right, this gives a clockwise motion. This also gives a clockwise motion. So there will be a clockwise torque, right, about the axis. This object here will start to rotate. So this object is not in equilibrium. Okay, actually these two forces, we say that they are a force couple, okay, which is two force equal in magnitude, parallel and opposite in direction. Like giving something pure rotational motion now, okay? It will just start to rotate. So for this topic, we'll be trying to solve static equilibrium problems. And then these are the general steps on how to tackle this kind of problems. Okay. First step, always, because forces are involved, right? Always draw the free body diagram. And this step is the most important. You must draw it correctly. Okay, free body diagram. Next step, choose your axis and directions properly. Okay, define your axis and your directions. And stick to it. Okay, I believe you all know that already. Okay. Then third is take summation of forces equals to 0. So usually we are doing with 2D, right? Which is got x and y. So x must be 0. Summation of forces in y also must be 0. Okay, so must fulfill this criteria. Then the last one is choose any point and take summation of top. Because we know static equilibrium, the criteria is summation of forces equals to 0. Summation of top about any point must be also equal to 0. That's why you will use this criteria to solve problems. So some points to note, which will be clearer later as you try to do examples. If a force has a line of action that goes through a point, the top of the force with respect to that point is 0, which is very useful to eliminate unknown forces and components. As we know already, if the force cuts through a point, if you judge the point, right, there will be no top around it, right? Because it's cutting through the rotation point itself, okay, the axis of rotation. So that's a very useful property. Need to draw forces at points where there is contact, when movement is restricted. So for example, at supports or hinges, right, you must always draw out some unknown forces, okay, which you will see later. No worries. Try to first solve for unknown forces, which are more straightforward. Simultaneous equations may be required at times. Many times it will be required actually. Okay, so come to one simple example first. A sports car has 53% of its weight on front wheels and 47% on its rear wheels. It has 2.46 meters distance between front and rear wheels. So if you draw a simple diagram, the front wheel here, the rear wheel here is 2.46 meters apart. And then the normal force down here is 0.53 W. Down here is 0.47 W because they already tell you what's the percentage distribution already. Okay, the whole thing, of course, you will have at the center of mass, right? At the CG also, you will have a weight that is pointing downwards. Okay, they ask you how far in front of the rear axle is the car's center of gravity. So they are asking you to find this LCG. Basically from the rear axle to the car's CG, what is the distance? So you'll be either taking summation of forces or summation of torque. Okay, down here, we just need to take summation of torque about point R. You'll be able to solve this already. Okay, so let's take a look. If you take summation, taking moments means take summation of torque. It's the same thing. About point R, you go and look at what are the forces that will come into effect. Okay, this force 0.47 W, it cuts through exactly at this point, right? So it will disappear from this equation. But if you really want to write out, right, it will be something like this. Force times the perpendicular distance, which is 0, right? That's why it will cancel out. So this is a very useful property to use to eliminate unknown forces. Okay, just saying. Then what other forces you have? You also have this W, right? So what is the torque that's caused by that? Is W times the perpendicular distance. Okay, that's why WLCG. And in this question, we take clockwise as negative. That's why there's a negative sign in front. Then what's the last force? Is your 0.53 W down here, pointing upwards. Okay, so it's a plus force times distance. Okay, then the whole thing must be equals to 0 because remember, summation of torque equals to 0. Cannot have any torque. So from this equation alone, right, you realize you already solved already. L you can solve for LCG. Okay, that one simple example. Let's take a look at more normal kind of example, okay? A diving board 3 meters long is supported at a point 1 meter from the end. And a diver weighing 500 Newton stands at the free end. The diving board is of uniform cross section and weighs 280 Newtons. Find the force at the support joint, which is here. Support joint is here. And then also the force at the left hand end. So the left hand end is here, support is here. Okay. So first thing you will do is go and draw a free body diagram of this scenario. Okay, you have a board. First thing easiest to draw is of course the weight. It will be applied at the middle where the CG is. They tell you 280 downwards, right? Then at the end where the diver is, they tell you the weight is 500 Newton. So draw is acting downwards. What other forces you have? There is also a support and at the left hand end. Okay, so this is what we mean by as supports or at fixed ends, right? You must draw unknown forces. Okay, because there will be unknown forces trying to hold the board in place there. That's why it's not moving anywhere. It's stuck at the support, right? Because of these reaction forces. Okay, so down here, draw one unknown force. You can either point up or point down is okay. Because you at this point of time, you don't know where is it pointing. Okay, but later your answer will tell you lah. If you get a negative value, right, means it's in the opposite direction of what you have drawn. Okay. So for this solution, we just define upwards F1 unknown. Then at the left hand end, right, we draw downwards. You also can draw upwards. But whatever you draw, you stick to it. You must stick to the direction and then solve assuming you are correct. Okay, at the end, then you will find out. So this diagram looks like this. Now we will start to do all your summation of forces, summation of torque. Okay, so you will first take summation of torque at point A. Okay, you can write it like this, summation of tau A. It must be equals to 0. So what forces do you have? You have F1 times your distance. You also have they do the 500 Newton first. You have the diver weight. Clockwise, right? That's why minus 500 times the distance from wherever you are pivoting. You are taking your summation about which point, okay? Then the last force is your 280 times your 1.5. Also, you will minus this value because it's clockwise, it's acting clockwise. The whole thing equals to 0. You see, you take a summation of talk about point A, right? Very strategically, you already eliminate F2 from this equation already. Okay, that's the useful part about taking summation of torque. You take at that point, right? Whichever force that act at that point will disappear from the equation. That's why you see this equation inside only got F1. Okay, then you just straight away solve for F1 already. So the force at F1, the force F1 is 1920 newtons, and it's a positive value, right? Which tells you that you draw pointing upwards, right, is correct. So the force of the support, right, acting on the board is pointing upwards, which makes sense because the diver press on the right, the support should be pressing up on the board, right? Should be pressing up on the board. Okay, so then you continue trying to solve for what is the F2, right? You will take summation of forces. In this case, a lot of forces in Y direction, right? So you take summation of forces in the Y direction. Basically, F equals to MA, but A is 0. So what are the forces you have? You have F1 pointing up, you have F2 pointing down, that's why minus, 280 pointing down, minus, 500 also pointing down, that's why minus. Okay, the whole thing must be equals to 0. From here, you can solve for your F2 because just now you already know your F1. F2 is the only unknown. So it will be equals to 1140 Newton. And down here, we get a positive value, right? Which means whatever direction you have drawn is correct. The force is acting downwards. Okay, so logically, you can also ask yourself, imagine the diver is standing here, right? At the left-hand end, the board will want to go up, correct? Will want to go up, but what force is trying to make it not go up? Of course, the force must point down, right? Yeah, so if you use this kind of logic, I mean, for simple cases, your brain can process this kind of thing, right? Then you realize pointing down is correct. But of course, if you have a super complicated one, then maybe our brain not so cannot process then you have to trust already Okay, but for these kind of cases, you see the board will want to rotate upwards, want to go upwards, right? She press down, the board want to go up here. So in order not to let the board go up, the left hand and the support, right, must be applying a downward force. Okay, so the direction is correct. F2 is pointing down. Okay, another example. Two people are carrying a uniform wooden board that is 3 meters long and weighs 160 newtons. If one person applies an upward force equal to 60 newton at one end, at what point does the other person leave? Okay, so you can draw a free body diagram. The board, right? You just draw one long line. Then one person carrying at the end, you draw one line pointing up at the end. Okay, the weight is always coming down from the middle. That's why you know this one is 1.5 because the whole thing is 3. Okay, then the other one is the unknown one. So they're asking you at what point, so what is X such that this thing can balance out? Okay, F1 they tell you is 60, they already tell you already. Okay, so for this case, right, you will be doing summation of forces in your Y direction, which will give you F1 plus F2, because they are both pointing up, minus W, because W is pointing down, must be equals to 0. Okay, so from here, you will be able to solve for your F2. F1 and W is known. They tell F1 is 60, W is 160. So from here, right, you already know that this force pointing upwards, it has a value of 100 newtons. Just that now you don't know where it is. Okay, but to find out where it is, you continue. You take summation of top, in this case, about the left-hand end. Summation of top about the left-hand end. You tell what kind of top, you ask yourself what kind of top involved. So what forces are there? Of course, you have this F2. F2 times X, that's the torque due to F2, minus W times 1.5. Definitely must be minus because they are in different direction. They are causing different direction kind of torque. Okay, so from here, you will be able to solve for your X. So now you know the value of F2, you also know what value is this X for this thing to balance out. Okay, so I will go through the supplementary questions with you all. Okay, because this lecture is short, but then because the concept is just nothing much, just that the concept is important, and then it's a lot about this free body diagram. So if you are very good with free body diagrams, right, you can draw free body diagrams very well. You should have no problem with static equilibrium kind of problem. Okay, but anyway, I'll just go through the questions with you all. A ladder carried by a fire truck is 20 meters long. The ladder weighs 2,800 Newton and the CG is at its center. Ladder is pivoted at one end, down here, about a pin. Ignore friction torque. The ladder is raised into position by a force applied by a hydraulic piston at C, down here. Point C is 8 meters from A. And the force F exerted by the piston makes an angle of 40 degrees with the ladder. So down here, this piston, right, will start to apply a force. But this force is at an angle of 40 degrees like this. They ask you, what magnitude must F have to just lift the ladder off the support bracket at B? So you can imagine originally, this support here, there will be some unknown force, right? Because it's a support. But the question wants you to find what must F be such that the ladder is lift off at support bracket B. When they tell you it's lift off support bracket B, right, means it's not in contact anymore. So when you draw the free body diagram, right, it's just that the support there, right, will not have any unknown reaction because it's not even touching anymore. Okay, that's basically the criteria you need to set for this question. So you will try to draw all the forces at the support. You will draw unknown forces, usually one in the vertical direction, one in the horizontal direction because you don't know. Okay, one in the vertical, one in horizontal. Again, the direction don't matter. You can draw upwards also. You can point left, up to you. But the sign later after you solve, right, will tell you if you need to solve. But for this case, don't need to touch this one, but still must draw out. You draw out, then weight, you draw out at the center. This force applied, right, is at an angle of 40 degrees. You draw out. So the free body diagram will just look like this. Okay, and to solve for F, you just need to take moments about point A. That means you take summation of top about point A. Okay, if you take summation of top about point A, you don't need to care about these unknown reaction forces anymore. Okay, that's the beauty of taking top about a certain point. All the reaction about at that point disappear. Okay, so what do you have? You have F pointing in this weird direction. But remember, torque is only the force that is perpendicular will be accounted for. Okay, so it will be F times 8 sine 40. You can see as this force multiplied by the perpendicular distance, or you can also see you go and resolve this F into one in the vertical direction, one in the horizontal direction. Same thing. Okay, if you resolve this F into one vertical and one horizontal, only the vertical one will play a part in the top. You realize the horizontal one will just pass through this point. Okay, so that's how you get this sine 40 thing at the left. Then what's the other force? You have 2,800 times 10 meter. Okay, so basically this equation alone will allow you to solve for F. Question 2, you're going to read on your own now. Okay, I'll continue with question 3. A 60 cm uniform 50 Newton shelf is supported horizontally by 2 vertical wires attached to the sloping ceiling as shown. A very small 25 Newton tool is placed on the shelf midway between the points where the wires are attached to it. Find the tension in each wire. So the ceiling is slanted. Then got 2 wires here, right? They ask you to find the tension inside. Okay, so this is the shelf, which has a weight of 50 Newton. You also have a tool here, right, in between the 2 wires. And they tell you it's 25 Newtons. So you go and draw a free body diagram of the shelf. Okay, free body diagram of the shelf. The shelf is not moving, right? So you draw a free body diagram of the shelf, then you treat it as a static equilibrium problem. So what do you have? The weight of the shelf, right, at the middle, acting downwards. You have that 2 wires pulling it outwards, right? That's why you got T1 and T2. You have another force pointing downwards. This comes from the small tool, the 25 Newton small tool. Of course, draw it at the right location. It's in between these 2 wires, right? So it's 20 here and then 20 here. Okay, so in total, you have these 4 forces. Then now, right, you can go and take summation of top and summation of forces to find your answers. It does not matter whether you take summation of torque or summation of forces first. Okay, you can take any. Then after you do already, you see whether you need to do simultaneous equation. So first thing in this solution, right, they go and take summation of torque about the left-hand side. That means about this, where the T1 will act through. Okay, then you can already tell, you go and take summation of torque about this point is purposely to eliminate T1 from the equation 1. Okay, so you see about this point, what do you have? You have this tool, this 25 Newton, weight of the tool pointing downwards times 0.2 meter, 20 cm is 0.2 meter. Then you also have the weight of the shelf times 0.3 meter. You also have your T2, okay, pointing in the upwards direction. That's why you will have different sign from the other forces. Okay, and that's 0.4 meters away from wherever you are taking the pivot axis. So in this equation, right, the only unknown is T2. So we go and solve for that, you will find the tension in this second wire, just from this equation alone. Then to find T1, very simple already, okay, because the other three, T2 is already known. You just have to take your summation of forces in the y direction. Okay, you have T1 plus T2, both pointing up. You have both weights pointing down, that's why minus. Okay, and equals to 0. From here, only T1 is unknown. You go and solve for your T1. Okay, and let's go through question 4 also. Find the tension T in the cable and the magnitude of the direction of the force exerted on the strut by the pivot in the diagram as shown. Let the weight of the crate be W. The strut is uniform and also has the same weight W. Strut is this rod thing. So this rod itself also has a weight W. It asks you to find the tension and also the unknown forces, magnitude and direction of the unknown force here. Okay, so go and draw a free body diagram of the strut. Okay, what do you have? You have a wire that's pulling, right? So you definitely will have a tension here. And just a reminder, drawing tension, right, means pointing away from the object, pointing away. Then there's a box hanging here, right? So you draw W pointing down. Then this strut itself also has a weight acting at its middle. So it's also another W. They tell it's the same weight. That's why this one also W hanging downwards. And then this one is the important one. At the ends, right, you will always have reaction forces. Now you don't know the reaction forces. That's why you need to draw them as unknown. Okay, so you draw one for the vertical, one for the horizontal. Okay, so you have 1, 2, 3, 4, 5, 5 forces, which you want to go and now do your summation of torque and summation of forces. So first thing we can do is summation of forces in the y direction. So we only have FB pointing upwards and W pointing down, W pointing down. The other two, they are horizontal forces, so they wouldn't appear here, right? This is for vertical. So you'll get FV equals to 2W. Then we continue. We can take summation of torque about point A. Summation of torque about point A. So what are the forces that will appear? First one is this T, right? This T times the perpendicular distance. What is the perpendicular distance? This whole thing, this strut, right, is length L. And we know here is 30. Correct? So will we be able to find the distance here? From point A to here. Yes, right, we can. It's just L sine 30. Okay, so the torque that's produced by this T is T times the perpendicular distance, which is L sine 30. Okay, then what other forces that are producing torque? One of them is this W, the other one is the other W. Okay, same thing, you will take W times the perpendicular distance. One is this one, the perpendicular distance for this will be L over 2 cosine 30, because we are actually finding just this distance, right? So W times L over 2 cosine 30, and also must account for the other weight right at the other end. Okay, just now it's L over 2, this one is L. So whole thing equals to 0. From here, you will get T equals to 2.6 W. Okay, so just now you get FV equals to something, now you get T equals to something. So what else you can do? You also can take summation of forces in the X direction. But this is nothing much because you do summation of forces in the X direction, you'll realize T equals to FH. In other words, FH equals to whatever you have found for T. It's the same thing. Because these are the only two horizontal forces. So they must be equals to each other. Okay, so FH must be equals to 2.6 W because T equals to 2.6 W. Okay, so you see from here, we already know FH is 2.6 W. We know FV equals to 2 W. That means these two forces, they are solved already. Can you find the magnitude and the direction? Yes, because all you need to do now is Pythagoras theorem and then use your trigo to find angle. Right, so basically these are two sides, one horizontal, one vertical. You want to find the magnitude, just Pythagoras theorem. You want to find where exactly this force is pointing, right? Just use your trigo to find the angle. Okay. Yeah, then question 5. Suppose that you can lift no more than 650 newtons unaided. How much can you lift using a 1.4 meter wheelbarrow that weighs 80 newton and whose center of gravity is 0.5 meters from the center of the wheel? They also illustrate for you nicely. So 0.5 meter from the wheel. The center of gravity of the load carried in the wheelbarrow is also 0.5 meter on the center of the wheel. Where does the force come from to enable you to lift more than 650 newton using a wheelbarrow? So we will draw a free body diagram of the wheelbarrow. At the right hand end, the wheel is in contact with the ground, right? So there will be a normal force pointing upwards. Then the weight is 0.5 meter from the end, right? They say both the load and the weight of the wheelbarrow is the same at the same exact location. Okay, then your F, you're pulling it upwards, right? So your F will be pointing up right at the other end, the left end. So with this, you can go and take your summation of torque, summation of forces. So summation of torque with the axis at the center of gravity, it will give you N equals to 0.5, N times 0.5, sorry, N times 0.5. We're thinking about this point, thinking about this point. Okay, so at the right, you have N times 0.5. At the left of it, you will have F times 0.9. Right, and the whole thing must be equal to 0. Okay, and then from here you can solve for your N, that means the normal contact force. Because you already know this F is whatever you can apply, right? And whatever you can apply is just max 650, they already tell you. Okay, so N equals to 1170, that's the normal contact force. After this, you'll just take summation of forces in a Y direction, which will give you F and N pointing upwards. That's why plus. Then the other two, right, is pointing downwards. One is the weight of wheelbarrow, one is the weight of the load. And the whole thing equals to 0. From here, you'll be able to solve for the load, the weight of the load, which tells you you can carry a load of 1740 Newton. So you see, you only need to lift 650 Newton, right? But you can carry a load of 1740 Newtons. Okay, so people come out with this kind of devices or mechanism to help them do work. Yeah, of course, these days is a lot of machinery and stuff, but people in the past, they use a lot of this kind of leverage to help them do more work. Okay, any questions? Okay, so today we only do until here, 14, 15, 16. Okay, then the supplementary questions, you all go and read on your own. Okay, then if nothing, can I just check whether there is Narayanasamy here, and also Gauri, are you here? Okay, I see Narayanasamy, but I don't see Gauri. Okay, so I'll just mark. Then if there's nothing, then I will see you all next week. Again, okay, next week is our last lesson. So next week we'll be doing 17, 18, 19. Okay, if you got any questions, you can ask me in the chat. If not, yeah, you can leave the chat already. Okay. Okay, thanks everyone for attending. You're welcome, Daryl. Yeah, welcome, Andrew. The final exam still don't know if it's online. Yeah, I wouldn't know. The admin, right, must email you all. Okay. But anyway, still sometime down the road. If it gets really too close, can email the admin to ask. Okay, by right, they should send you all an email to tell you all the instructions. The assignment need to have the school cover page thing. Good to have but honestly, because I mark, right, I won't be marking the cover page but it's always a good practice to have a nice cover